Okay, we continue with the second half of the video on section 1.4. In question 6 here, we have some carbon 14 dating. And it says after some ancient bones were excavated, carbon was taken from one of the bones to find that there was 75% as much in there as from current bones. And so, because of this, they were able to determine the decay constant to be given there by K that we see in the problem. So, how many years old is the bone? All right, so that's what we're looking for. All right, so for decay, we have the relationship for the differential equation here. N of T is the amount of carbon at a particular time left. Negative proportionality constant because it's going away. At time 0, we started with a particular amount. So the solution to this differential equation is a negative exponential. K is the rate of decay. So I'm going to let P times N0 be the percentage of whatever amount is left after time t. So 95% of N0 would be 0.95 N0. So what I do is I set this equal. The percentage left is going to be given by this formula. I can divide both sides by N0, and so I find that the percentage is given by this. If I take the natural log of both sides, I have the ln of e to something, but because they are inverse functions, I get a minus kt. And so what I do by this is I get a formula for time where I could plug in any percentage that I liked along with k, and I could find out how long that was, rather than just sticking in the number from the start. So I like to get a formula. That way I can use that for multiple instances or for analysis purposes. All right, so what do we want? We want the percentage to be 75%. And so if you plug all that in, you get about 2,366 years, because they said round to the nearest year. All right, in this problem, problem 7, we have a couple, and they deposited $6,000 in an account that pays 7% interest compounded continuously. All right, so taking a look at this, the differential equation for this, we have a positive r here because the amount is growing, unlike the other problem we just did where it was negative and decaying. So what you see here is the typical formula for the compound interest done continuously. So R is our rate of interest. T is time in years. We have 7% interest. We initially deposited $6,000. So how much money will be in there if we wait a time of 18 years? So mainly just grinding away with your calculator. We've got 21,152.5289, but then you round this to the nearest cents, and so 52 becomes 53. All right, question 8. The wording here is a bit strange. So we have a mineral body, a rock, and the rock contains some amount of uranium-238. And they're telling me that it has a half-life of this number. But currently there's no lead in the rock. Why do we care about all that? Well, the rock has some uranium in it. As it decays over time, it's going to produce lead. So if the ratio of lead atoms today, the ratio of uranium to lead is 0.35, how long ago did the mineral body form? All right, so this is a radioactive decay. That much is fairly straightforward. N0 is the amount that we initially start with. We have a half-life. Half-life means half of it goes away. All right, so why am I plugging this in? All right, so I'm trying to figure out what is this decay rate. All right, so putting all that in, we get this number for K, for half of it to go away. All right, so plugging in the half-life time, I can find out the rate. All right, so I've got K now. So let's take a look at the wording here. At time 0, we have this rock, a mineral body, has some amount of 238 in it. All right, so looking at my rock here, time 0, it's got some 238 in it, and at the moment it has no lead. So over time, the uranium will decay from whatever is in there at time 0. We've got K, we know the half-life, and the byproduct is going to be lead. So if you look at the graph here, N0 is my uranium. The uranium is decaying. The amount of lead is in there, initially none. Over time, it begins to grow. So if I look at a particular time, here's the amount of uranium 238 that I've got at time t. Here's my lead. Now, well, what is the amount of lead? Well, the amount of lead is going to be whatever we started with uranium minus what we have currently, and the amount left in there will tell me the amount of lead at this time. All right, so all of that's here in the verbiage. All right, so let's see. Now they're telling me the ratio is 0.35, and that's the ratio of the amount of lead right now to the amount of lead now. Okay, so the top is based on my decay formula of uranium. The amount of lead that is growing is whatever amount of uranium we started with minus the amount of uranium we have currently. All right, so I factored out N0 e to the minus kt. Why did I do that? Because I'd like to get this thing to cancel. So, all right, looking at that, I've got 1 over e to the kt minus 1, and that equals the ratio we were given. What is it I'm trying to find? Well, I know K from before. I'm trying to find the time. All right, so plugging all that in, we can distribute, start trying to isolate e to the kt. All right, so now I need to get my hands on time. So I'm going to take the natural log of both sides. The natural log of e to the kt is kt, and then divide by the k. So here's the amount of time. So plugging in all the numbers, all right, so here's my k that I solved for. I'm trying to keep everything as many digits as I can, and then I'll round it in the end. All right, so this one will flip. It's up on the top. So now I've got this number times ln divided by the natural log of 2. And so we get 8.78 times 10 to the ninth years. So kind of a tricky problem with the wording. In question 9, I've got some buttermilk, and we've set it out to cool on the front porch. The temperature there is 0. The milk was originally at 81 degrees C. All right, so we start off 81 C is cooling down to the porch at 0. All right. We know that it's cooled to 73 degrees, 73 down, after 28 minutes. Now they have to give us that information because we need to know what is the decay rate or the proportionality constant K. So how long will it take to then go from 73 down to 61? So our differential equation for Newton's law of cooling. All right, so here's K. A is 0, outside temperature. And so we get this simple differential equation, which I've got now my decay rate, T0 e to the minus kt. T0 was the initial temperature of the milk. All right, so I've got that. I can find out what K is because I know after 28 minutes, I'm down to 73 degrees. So grinding through all that, I can figure out what's K. All right, now that I know K, all right, I can plug in my 61, and I'm looking for T. All right, so doing that, I've got the ln of 61 over 81 divided by negative K. Here's my K. So plugging all that in, and again trying to keep it as accurate as possible. Flip this bottom. It's on the top. And now we can grind away and calculate this. And so T is about 76 minutes to go from 81 degrees down to 61 degrees. All right, in question 10, we've got a spherical tank. It's a ball. It's got a radius of 5 feet on the tank. It has a circular hole in the bottom. So the tank is a sphere. Cross-sectional area is a circle. The bottom hole here is 4 inches. All right, so the question is this: using Torricelli's law, how long will it take for the water to drain from the tank? Acceleration of gravity is here 32 feet per second squared. All right, so the question is, how long in minutes? Minutes. All right, so notice I've got to worry about units here. Let's see, because I've got feet here on the tank. I've got inches there, feet here, and gravity, seconds, and minutes. All right, so Torricelli's law looks like this differential equation. And so what's all this junk here? A of y. A of y is the cross-sectional area of the tank at a particular depth y. A is the diameter or the radius of the hole in the bottom of our tank. G is gravitational constant that they gave us. All right, so looking at the picture here, here's my tank, circular tank. Here's the depth y, At a particular depth, there is a cross-sectional area. Okay, so initially nothing starts to get bigger. Here, when I get down to halfway mark, so y is halfway, then I have a full circle, and then as we begin to get lower, again, here's y. There's my cross-sectional area. All right, so again, so initially, the full thing is 10 feet. We start coming down and down. All right, so if I look at y of t over time, that's the height of the water in the spherical tank. The height is going down. All right, A is my area in the bottom of my tank. All right, so here's my area, A. My hole is a 4-inch radius. All right, so I need to convert. So 4 divided by 12, so 1/3 foot. And so the area of my hole is 1/3 squared times pi, so pi over 9. All right, gravitational constant, time is in seconds. So A, as we talked about, is the cross-sectional area. Okay. All right, so let's take a look at what this looks like. So if the height is up to here, so here's the radius of the tank, because that's from the center out, that's 5. This is 5. And if I look, here's the radius at a particular height. We get this little part that's in here, and this little part is either y minus the 5 under it, or if the level of the water is under the midway point, here's y. This is the 5 point, and the little green part is 5 minus y. So either way, it's either y minus 5 or 5 minus y, depending on the height of the water. All right, so the Pythagorean theorem will give me some information about r. And so what I did was I compared by doing it either way. In either way, I get the same formula for r. All right, so A of y is pi r squared, my cross-sectional area. So I've got an r squared that's the same, so I don't have to worry about that it's different in different places, so the same formula. All right, so the area starts off at 0 when we're full. As we go down, we get maximum area at 5. And at the bottom, well, when y is 0, area is 0. When it's full, it's also 0. Y is the depth in the tank. All right, so plugging all this stuff in, here's my formula. Cross-sectional area, the area for the hole. We've got the gravitational constant. 2 times that is 64. That's nice because the square root is 8. All right, still grinding, still cleaning up. So at this point, I'm trying to make it into a separable equation. All right, the right-hand side is easy. That's a minus 8/9 t plus c. The left side, I need to separate this and use my rules of exponents. This is y to the 1 over y to the 1/2. 1 minus a half is a half. 2 minus a half is a 3/2. And so now we can use our power rule to integrate each piece. All right, so looking at this, I need to clean this up. All right, so I'm cleaning it up by multiplying through. All right, so I've got this, flip it over, 2/3, flip this over, I got 2/5. So at a time of 0, y0 is full, so that's 10. So each of my y's is 10 times 0. And so I can grind through this and I can find out what's c. All right, so when the tank is empty, the height of the water is 0. All right, so where are we at here? All right, so y is 0, so I've got all that. Plug in this stuff for c and for y of t. I'm solving for t, the time, when the height is 0. Again, a lot of grinding. I'll let you go through that slowly. And eventually we get 94.868 seconds, because remember we had the gravitational constant. It was in terms of seconds, so the time I solve for is in seconds. I need to convert it to minutes, so divide by 60 seconds. And I get the time for the tank to completely drain is 1.58 minutes. So as you can see, separable equations by themselves can be easy, but when it gets to the practical applications, things get messy and difficult.